acid derivatives contain a carbonyl, at least most of them do. And so acid derivatives actually are they're weak electrophiles, and they react well with strong nucleophiles. And the most common strong nucleophile that we've talked about with regularity are organometallic species. So I want to talk briefly about how acid derivatives react with organometallic compounds. And the fact is, almost all acid derivatives react with organometallics in some way. But mostly I want to focus on how esters react with organometallics. Oops, that's an E. Metallics. Great. So let's take an ester and let's make it, let's just leave it R, that's fine. And let's react this with an organometallic reagent. Now, as it turns out, we're going to need two equivalents. So 2 times some generic organometallic species. And let's write an organolithium. You can use Grignards here as well. But we're going to react it with an excess of the organometallic reagent. Well, this is a strong nucleophile. And we're going to react it with our weakly electrophilic ester. Bam. Attack. Of course, what we get will be a tetrahedral intermediate. Oh, you know, that's not nucleophile. That's R double prime. Okay, once we make a tetrahedral intermediate, when we're in the realm of acid derivatives, and we're talking about esters, we look for a leaving group. Now, OR would never be a leaving group back when we talked about SN2 reactions. But leaving groups, just like nucleophiles, depend on the context. As it turns out, an OR group is just fine as a leaving group. So we kick that out. We lose that as an O-, no problem. And once we eject our leaving group, we get a ketone. Well, we are not done, because ketones also react with organometallics. And because we use 2 equivalents of our organometallic reagent, we're going to attack again. So this is an anion. It attacks the carbonyl. And we get, yet again, another tetrahedral intermediate. And now we don't have any more leaving groups. Our R groups, all 3 of these are going to be some kind of carbon group. They are stuck on that carbon. They're not going to get pushed off. So now our tetrahedral intermediate, like we saw earlier in the course, it just hangs out. Hangs out until we do what? Hangs out until we add water. Now, it's kind of a quiz question. Why don't we have water in this reaction? Well, we don't have water to start with because we're doing organometallic chemistry. And organometallics can't exist in the presence of water. They're too basic. It's a strong nucleophile and a strong base. And water will protonate it. So this addition of water will have to be a second step. So here's our final product. We get an alcohol from our ester. And if we were writing this out as a reaction, we'd write it this way. Step 1, we'll treat with our organometallic reagent. You might write excess next to it to mean you need extra, or you might write 2 equivalents, whichever. And we'll need a second separate step of water. And what we get is this alcohol. Now, if you're keeping track, we get another alcohol, actually. We get the alcohol that comes from this group that was ejected. Normally, this product is the focus of our reaction. You know, we did this reaction on the carbonyl. We want to keep that carbonyl carbon. Sometimes it's this group that actually is what you want. So it just depends on what you're looking for. But note that there is another product here, and that it contains carbons, and sometimes that's of interest as well.